Okay, here we are with, I'm just grouping all of section 5, 6, 8, and 9, I believe, together into one grouping. And we're going to be looking at irregular cross sections, meaning not circular, thin-walled sections, and stress concentrations. So we have a shaft. It's made of red brass, and it has an elliptical cross section. If it is subjected to the torsional loading, determine the maximum shear stress within each region and the angle of twist of end B relative to A. So we have done problems very similar to this with a circular cross section. So remember, with a circular cross section, our shear stress is TC over J, and our angle of twist is TL over JG. When we move to non-circular cross section, so this is what we've spent, the past 4 days lecturing on, then we actually have additional equations. And in our textbook, we can actually get a table. And from that table, I can find the elliptical shape. And when I look at the elliptical shape, it is defined as A, B, B. So this is going to be my longer, okay, my longer segment and my shorter segment. So coming back down here, I can see that A equals 50 millimeters, which I don't want to work in, so 0.05 meters. B equals 20 millimeters, which is 0.02 meters. So I'm going ahead and I am getting these based off of that chart. The other thing is that when I look at the maximum shear stress for an elliptical solid, it is 2 times the internal torque pi a b squared. When I look at the angle twist for a cross section like this, it's going to be a squared plus b squared times TL divided by pi a cubed b cubed g. So that's what I'm going to be using. Well, the first thing we have to do is figure out what are our internal torques. So I'm going to start at the left. I'm going to draw my cross sections and I'm going to cut. I'm going to cut, figure these things out. So I have 50 Newton meters coming towards me. I'm going to assume positive internal torque from A to C. Positive by right hand rule if I make a cut, but if my hand goes on that cut, coming towards me is positive. I can now sum my torques. I'm going to just say coming towards me is positive, and I can, when I sum those up, I'm going to find that TAC equals negative 50 Newton meters. Now I'm going to come through and make my cut, and remember we have to show everything to the left or to the right. So I have 50 Newton meters coming towards me. I have 20 Newton meters going to the back, and I'm going to assume that internal torque from C to B as positive. And then I'm going to sum my torques coming towards me. I'm going to call positive for equilibrium. So I have 50 minus 20 plus TCB equals 0. So TCB equals negative 30 Newton meters. So now if I wanted to draw a torque diagram, then as I'm coming from A to C to B, my internal torque in Newton meters, I have negative 50, and then I have negative 30. So if this were all, if we were trying to do design work, I would need to make sure that I looked at this segment because it does have that maximum internal torque. But it's just asking us what is the shear stress within each of them. So I have my equation, and now it's just a matter of plugging things in. So the shear stress from A to C equals 2 times negative 50 Newton meters divided by pi times A, okay, 0.05 meters times B, 0.02 meters cubed. So the shear stress from A to C is 250 times pi as a number, 0.05 times, 0.02 times, 0.02 times. I think that's supposed to be just squared. Looking at units, it's going to be Newton meter. meters cubed, so Newton meter over meter cubed is Newton per meter squared, which is a Pascal. So units, always the best thing ever. Then, so I get this very large number, and we're going to work it back 1 to K, 1 to M. So my shear stress is 1.59 megapascals. That would be a Newton per meter squared. And we can find the shear stress from C to B. And I'm going to get 2 times negative 30 Newton meters divided by pi, 0.05, 0.02 squared. So we have 60. And then we have pi as a number, 0.05 times, 0.02 times, 0.02 times, divided by 1, 2, 3, 4, 5, 6, 0.95 megapascals. So there are my shear stresses. And then I want to know, so we could also graph those. Here's my shear stress, megapascal. And I'm going to have, these are both negative, 1.59 and 0.95. So as long as this one is not yielding, nothing else is yielding because it's the largest one. So we would need to go back and check to make sure that we didn't have yielding. Now for angle of rotation, I want to go from A to B because I want to know B relative to A. So when we are looking at B relative to A, we are going to have phi from B to C plus phi from C to A equals, here's my equation for both, and they're both negative, so they're both going to be twisting the same direction. So I have negative, and I'm just going to put a negative, well, I'll just put a negative in for the t to be consistent with math. Okay. You know what I am going to do? Because this segment is all the same A and B and A and B and G, I'm going to pull out this nonsense. This is how I'm going to simplify my life because I don't like writing a bunch of stuff. Simplify our life. And I'm going to pull out A squared plus B squared times, well, T and L are different, divided by pi over A cubed B cubed G. Then I'm going to go back in and get my TL. So I have negative 50 times 2 meters plus negative 30 times 1.5 meters. And we have simplified our life by pulling all of that stuff out. So when I'm looking at A squared, 0.05 squared plus 0.02 squared divided by pi, 0.05 to the cubed, 0.02 to the cubed. And then we would need to go to our handy dandy chart in the back of the book. And when we did that, we would find that G is 37 gigapascals. So 37 times 10 to the 9th. Negative 50 times 2 minus 30 times 1.5. And I'm going to get then that my angle of twist from B to A is negative 0.00249 radians. Okay, now if I wanted to sketch that, from A is where we would be going, calling 0. And then we would actually find the angle of twist for this section, which I know is negative. And then we would find the angle of twist for this section, which is going to be flatter because number one, it's shorter and it has a smaller internal torque. And so this total value is going to be that 0.00249. But if I had done these individually, I would have gone from 0 and then I would have, this number here would have been the angle of twist from A to C. And then I would have added on, and this would be this whole equation right there. And that's how my angle of twist would look. It's all going to be twisting negatively.